start discussion on a new topic which is called potential flow. So, this is a topic where we are going to look at incompressible and irrotational flows. Now, you have seen that incompressible means that your conservation of mass reduces to divergence of V equal to 0, where V is your velocity vector. And you have also seen that irrotational means that the vorticity, which I will denote by small omega, which is the curl of the velocity field, this is equal to 0. Now, you know that a necessary and sufficient condition for the curl of a vector to be 0 is that V be the gradient of some scalar. So, this quantity is this function which I have written as phi here is what is called velocity potential. And the name potential flow is coming because the velocity can be described by a potential. Now, we will be looking at 2D potential flows, but before that I will just recapitulate something which has been done earlier. We know that curl of grad phi is identically equal to the 0 vector. So, if V is the gradient of a scalar function phi, then it is this velocity field is going to be irrotational. Now, you can also show that this is also a necessary condition for a velocity field to be irrotational. Now, if it is 2D, you can define a stream function. If it is 3D, you can define what is called a velocity vector potential, that is, you can write V as curl of some velocity field, and this is a vector stream function or vector potential or whatever we call it. But we will not be looking at 3D flows. So, we will concentrate on 2D incompressible flows. We will look at 2D potential flow. Now, 2D means I can choose a coordinate system such that the gradients with respect to one coordinate, say z, of any flow quantity is 0, and the velocity component V z in that direction is 0. So, the velocity vector then I can write as V x I plus V y j, and also you have V z k in general, but we are dealing with a flow situation where V z is 0. Now, we will switch over to another notation because writing subscripts is a cumbersome way of dealing with things. So, we will write V as u I plus V j, where this V should not be confused with this vector V. This V is the y component of the velocity and this u is the x component of velocity. Now, if it is 2D, then we will say and steady, then u will be a function of x and y only, and V will be a function of x and y only. So, this is for 2D steady flows, and W is 0 at all points. And if you look at the modified pressure or the static pressure, this will be a function of x and y only. Now, if you have 2D unsteady flows, then u, v and p can depend on x, y and t as well. Now, first of all we will look at the vorticity vector. I am denoting this by the symbol omega. So, this is the curl of the velocity field. So, in Cartesian coordinates you can express this by the determinant, where in the first row I write the unit vectors I j k, in the second row we will write the components of this first vector, which we view as a grad as a vector operator. So, grad is going to be viewed as I del del x plus j del del y plus k del del z. So, here we will write del del x, del del y, del del z, and the third row will be the components of the second vector, which is v. So, that we will write as u v w, and in this case w is 0. So, we will write 0. Now, if we expand this, you are going to have the I component will be minus del v del z. It is actually del del y of 0, which is 0, minus del v del z, but we are saying that del del z of any flow quantity is 0. So, this is 0. Similarly, if you look at the j component, you are going to have del u del z j. So, it is minus I minus j times this subdeterminant. So, it will be plus del u del z j, and this also is 0 because there is no variation in the z direction. So, curl of v will have only one component, which is the k component. So, it is k times this subdeterminant. So, we are going to have del v del x minus del u del y. So, if you have a velocity field v which is of this form, u of x y I plus v of x y j, then the corresponding vorticity vector, which is defined as curl of the velocity field, I can write as omega x I plus omega y j plus omega z k. What we are finding is that omega x is 0, omega y is 0. So, if the flow is in the x y plane, so this is called a flow in the x y plane. This statement means that you have only a v x and a v z y component of velocity. The v z component of velocity is 0 and there is no variation in the z direction. It is not that the flow is occurring in a plane, the flow is occurring in a 3D volumetric region, but we mathematically you have only a v x and a v y, which here I am calling u and v, and they depend only on x and y. In that case, what you find is that only the z component of vorticity is non-zero. That means I can write omega vector as omega z k. So, it means that the vorticity vector is perpendicular to the plane of the flow. Vorticity vector is perpendicular to the plane of the flow. Now, since this there is only one component of vorticity, I can, if you look at the magnitude of the vorticity, this is going to be simply magnitude of omega z, and we will adopt this notation that omega vector will write as omega k. I am dropping the subscript z. There is no confusion because we know for this flow that omega x and omega y are 0. So, if I am talking about a vorticity, it is the z component of vorticity, and we have seen that omega is del v del x minus del u del y. So, if the flow is irrotational, then omega is 0. So, irrotational flow, 2D irrotational flow means that omega z is 0, which means that del v del x minus del u del y is 0. Now, let us write down the mass conservation equation for 2D incompressible flows. Now, in this case, if you look at divergence of V in Cartesian coordinates, you can write it as del u del x plus del v del y plus del w del z. So, this is going to be equal to 0. So, this is a general equation for 3D incompressible flows. We are looking at a case where this term is 0, identically 0. That means del u del x plus del v del y equal to 0. So, when we talk about 2D potential flows, the velocity field satisfies two conditions. One is del v del x minus del u del y equal to 0, and the other is del u del x plus del v del y equal to 0. The second equation is a consequence of the local conservation of mass for 2D flows which are incompressible, and the first one is a consequence of the fact that the flow is irrotational. Now, from these two equations with appropriate boundary conditions, one can determine the velocity field, and then you can go to the momentum equations to find the pressure. And it has already been shown that when you have irrotational flows which are incompressible, the momentum equations can be integrated, and the integral is your Bernoulli's equation. So, if you look at the Bernoulli's equation, you are going to have P plus half rho v squared plus rho g z equal to constant. So, we are dealing with flows which are steady. This density and this density which is appearing over here, we are assuming to be constant. So, rho equal to constant. And we have considered a flow field where the only body force is due to gravity, that is called a conservative force field, and in addition we are assuming that the flow is irrotational. Now, when the flow is irrotational, you can apply Bernoulli's equation between any two points in the flow field. They need not be on the same streamline, as in the case of inviscid steady constant density flows, which means that this constant is a global constant valid for all points, whereas in the case of inviscid flow which is rotational, if it is steady and incompressible, you can apply this equation, but this constant varies from one streamline to another. Now, of course, the moment I write this equation here, I have assumed that my notation is that z points vertically upwards. So, if this is the direction of the gravity vector, then I have taken a coordinate system where z axis is vertical and pointing upwards, and the xy plane is the horizontal plane. Now, if you want to write it the same expression in any other coordinate system, you can write it as p plus half rho, and this you can write as v dot v minus rho g dot r equal to constant. So, here you can, the z axis need not be vertical. Now, what we see is that the relation between p and v is nonlinear. You see, p goes as v squared. The momentum equation was nonlinear. So, when you integrate it, you have a nonlinear relation between pressure and the velocity, but when the flow is irrotational, it was shown that those equations can be easily integrated, and this is an algebraic relation. So, if somebody can find the velocity field, then finding the pressure from this equation is a straightforward job. Now, the reason why we study potential flow is that in this particular case you can find the velocity field by looking at this equation and this equation. Without looking at the momentum equation, one can solve for the flow field by using the irrotationality condition and the incompressibility condition. So, that is what we are going to do. Now, you can have in special cases viscous irrotational flows also, but that is a matter of research topic, we will not discuss it here. In most cases, you may vorticity can be generated by viscous actions. So, people when they talk about irrotational flows, they imply that the flow is also inviscid. So, first I will show you how to solve these equations, and then I will discuss the conditions under which the flow can be irrotational. So, you will see the utility of studying 2D potential flows when you in real life. So, let us go back and look at the two conditions which we have. The first one we wrote as del v del x minus del u del y equal to 0. So, we will call this equation number 1, and the second equation is del u del x plus del v del y equal to 0. Now, let us introduce the velocity potential. So, if I say the velocity potential is the function phi of x y, let us say, then you know that u is del phi del x, this is the x component of velocity. So, x velocity is the x gradient of phi, and the y velocity, which we are also referring to as v, is the y gradient of the same function. Now, some authors may put a minus sign in both the equations, that is just a sign convention, it does not matter, it can be absorbed into the phi, but both the equations have the same sign. Now, if we take this definition of u and v and look at the first equation, so let us look at now left hand side. Of equation 1, that is del v del x minus del u del y. So, this we can write as del x of del phi del y, where I have used this relation that v is del phi del y, minus del y of del phi del x. So, here I have used the fact that u is given by del phi del x. Now, the first term here is del 2 phi del x del y. So, this is the mixed partial derivative, where first you are differentiating with respect to y and then you are differentiating with respect to x. And the second term we can write as del 2 phi del y del x. So, this is also the mixed partial derivative, but here you are first differentiating with respect to x and then with respect to y. Now, you know from your course on calculus that these two are going to be equal if phi del x and del phi del y are continuous functions. So, this is going to be identically equal to 0 if phi del x and del phi del y are continuous functions. Now, can we find such a function? Well, for this case we can use the second equation to find this function. So, let us look at the left hand side of equation 2. LHS or left hand side of what I have labeled as equation 2 is del u del x plus del v del y. So, this is the divergence of the velocity field, which is a scalar. Now, this I can write as del x of del phi del x, where I have used the fact that u can be expressed as del phi del x. And then you have the second term, which is del y of del phi del y. So, this left hand side I can write as del 2 phi del x squared plus del 2 phi del y squared, and equation 2 is del u del x plus del v del y equal to 0. That means that phi must satisfy the equation del 2 phi del x squared plus del 2 phi del y squared is 0. And you may recall that this equation is associated with the name of Laplace. So, this is the 2D Laplace's equation. Now, the momentum equations were nonlinear and it is not easy to solve nonlinear equations, but you can see that this equation is a linear partial differential equation. So, if you can solve this equation, you can find the scalar potential phi, and once you have the scalar potential, you can find the velocity u simply by differentiating it with respect to x, and you can find v by differentiating the same function with respect to y. And once you have u and v, you can find pressure using this relation p plus half rho. Now, v square will be u square plus v squared, because that is the magnitude of the velocity squared. And if I use a coordinate system where z is vertical, then plus rho g z equal to 0, or you can write it as minus rho g x x plus g y y plus g z z equal to constant. So, the procedure for finding the flow field becomes straightforward. You can find the velocity potential by solving a linear equation, find the velocity simply by differentiating, and then you find the pressure from Bernoulli's equation. Of course, the relation between p and v is still nonlinear, but it is an algebraic equation, and if these are known u and v, then finding p is a straightforward matter. Now, we will take another route and introduce the stream function. So, what we had done earlier was, by introducing the velocity potential, we made sure that the first equation was identically satisfied, and that function we obtained by enforcing the second condition. Now, we will introduce a stream function which will identically satisfy equation 2, and we will find that stream function by enforcing equation 1. So, if we recall, the x velocity for 2D incompressible flows, or the u velocity you can write as the y gradient of some scalar stream function psi. So, V x is the y gradient of psi, and V y, which we are calling V, you can write as the x gradient of psi, and one of the two equations must have a minus sign. So, I will put a minus sign here. If you want, you can put the minus here and then put the plus here, but both cannot have the same sign. So, psi is called a stream function. The reason it is called a stream function is that psi can be shown to be a constant along a streamline. Now, if you go back to this equation, which I have called equation number 2, the left hand side of equation 2, which is del u del x plus del v del y, now I can write as del del x of del psi del y. So, here I have used the fact that u is del psi del y, and the second term is you have to add to this del del y of minus del psi del x. So, here I have used the fact that the v velocity here is minus del psi del x. So, this I can write as del 2 psi del x del y, the mixed partial derivative, where I am first differentiating with respect to y and then with respect to x. The other term, because of the minus sign here, I can write as minus del 2 psi del y del x. So, this is a mixed partial derivative where first you differentiate with respect to x and then with respect to y. Now, once again, if psi del psi del x and del psi del y are continuous functions, then this is going to be identically equal to 0. So, the condition here is that psi del psi del x and del psi del y are continuous functions. So, if we introduce a stream function and define the velocities according to this, then equation number 2 is analytically satisfied, and that function you can find from equation 1. So, let us now look at left hand side of equation 1. Left hand side of equation 1 is del v del x minus del u del y. This is the vorticity, which is 0 for this case. Now, this I can write as del del x of minus del psi del x, where I have used the fact that v is minus del psi del x, and then you have a minus sign here and you have del del y acting on del psi del y. So, these two terms I can write as minus del 2 psi del x squared minus del 2 psi del y squared. Now, if I factor out the minus sign, you have minus the 2D Laplacian of psi del 2 psi del x squared plus del 2 psi del y squared. Now, this quantity by definition is actually the omega z, the vorticity component. So, this is a general relation between stream function and vorticity for 2D flows, but here for potential flows this is equal to 0. So, what we see is that if the right hand side is 0, the minus sign drops out, and psi also satisfies Laplace's equation in 2D. Del 2 psi del x squared plus del 2 psi del y squared will be equal to 0. So, this is Laplace's equation in 2D. Where you do not have the third term del 2 psi del z square, because psi depends only on x and y. Now, again this is a linear partial differential equation. Now, linear equations are easier to solve than nonlinear equations, and it is possible to get analytical solutions. Once you have determined psi, you can find u by looking at finding what is del psi del y, and you can find v by differentiating psi with respect to x and putting a minus sign, and then you can go back and substitute into this equation to find the pressure. So, the reason we study potential flows is that you can find analytical solutions easily. So, you solve either Laplace's equation for the velocity potential, or you solve Laplace's equation for the stream function to find the velocity field, and then you can find the pressure from Bernoulli's equation. Now, although the equations for phi and psi are same, the solution will not be the same. The reason being the boundary conditions are going to be different. For example, if you consider a flow over a plate, so let us say this is a plate which is impermeable. If I say this is x and this is y, then you know that the normal velocity at the plate will be 0. So, v of x comma 0 is going to be 0. So, this is the this 0 means this is at y equal to 0. Now, in terms of psi, I can write this as minus del psi del x of x comma 0 equal to 0. So, this holds for all x along the plate. So, if it is an identity in x, I can integrate it with respect to x, and the integral will be psi x 0 is a constant. If you have difficulty in following this, take this expression and differentiate it both sides with respect to x. So, del psi del x will be del x of a constant which is 0, which will means that if this psi is a constant along the wall, then the normal component of velocity is 0. So, here psi is constant. Now, the same condition I can write in terms of the velocity potential. Your u I can write as del phi del x, and v we can write as del phi del y. So, these two equations give a relation between phi and psi, and if you have taken a course on complex variables, you can define a function which is phi plus I psi, and this function will be an analytic function of z, where z is x plus I y, and these equations are called the Cauchy-Riemann conditions. You will recognize this as the Cauchy-Riemann conditions for f z to be an analytic function. Now, if you are not familiar with complex variable theory, you need not worry about this, because we do not need it for the rest of what we are going to do. But anyway, let us look at the definition of v in terms of the velocity potential. So, this quantity here, this you can view as a boundary condition, which I am writing simply as B c for solving the equation. You can write as del phi del y of x comma 0 equal to 0. So, along this plate psi is a constant and del phi del y, which is the normal gradient, is equal to 0. So, if you solve Laplace equation for the velocity potential, you will have to use this as a boundary condition at the solid surface, and if you solve Laplace's equation for the stream function, then you have to use this boundary condition psi equal to constant. And Professor Chakraborty has shown that the lines of constant psi and lines of constant phi, they intersect at right angles. Now, before we go further, let us see under what conditions a flow can be irrotational or where a flow is irrotational. So, I will take an example, simple examples of irrotational flows. So, simplest example is a uniform flow, that is u of x y is a constant everywhere. So, I will use the subscript infinity, because this typically is a boundary condition when you solve for flow over external flow over a body, and the subscript infinity reminds you of the fact that you may have such a flow far away from the body, and we have v of x y is 0 and w of x y equal to 0. So, this is a uniform flow in the x direction. Now, you may have a flow where the velocity profile is like this. Now, if you have a coordinate system where x is this way and y is normal to this, then this flow is described by this statement which I have written, u of x y equal to infinity, and I have deliberately drawn an inclined coordinate system to tell you that if you have a uniform flow, you can always choose a coordinate system with one axis along the flow. Then what will happen is the other component of velocity normal to it will be 0, and anyway the third component of velocity which is normal to this plane is 0, because we are looking at 2D flows. Now, if I take another point say here and draw the velocity profile, it is going to be the same uniform flow. So, if this is u infinity, this also is u infinity. So, this u equal to infinity is not at one point, but at several points. So, that means that del u del y is simply del del y of u infinity, which is a constant. So, this is 0. So, if you look at omega z, which is del v del x minus del u del y, that is del del x of 0 minus del del y of u infinity. So, this is 0. Now, I will take another counter example where you have say entry flow in a channel, and in the experiments when you do if you do experiments in the lab, typically a velocity profile may have this shape. So, here this is some u equal to v naught, let us say. If I say this is x and this is y, here this uniform profile is only at one section. It will not be uniform when the fluid enters the duct. So, this may or may not be irrotational, it depends on what is the v component. So, if I say u is v naught and v is 0, w is 0 at say x equal to 0, then here omega z is del v del x minus del u del y. Now, if you want to find omega z at y x equal to 0, you are going to have del v del x at x equal to 0 minus del u del y at x equal to 0. Now, this is 0 because at x equal to 0 for all y u is v naught. So, I can differentiate this. Now, we are saying that v is 0 only at x equal to 0, we do not know what is v at other x. So, this quantity need not be 0. So, this need not be equal to 0 necessarily. So, just by drawing a uniform profile you cannot say whether it is irrotation or not. You have to make sure that at several points in a certain neighborhood u is 0, so that you can differentiate this in that region. Now, we will look at a practical example. High Reynolds number flow over a flat plate. So, this is an example which we considered yesterday when we looked at boundary approximation. So, we will revisit this problem. So, let us say you have a plate and upstream you have a uniform flow. The plate is aligned with the direction of the flow, and we will take a coordinate system where the x axis is along the plate, y is normal to the plate, and the origin is at the leading edge. Now, if I say that this length is L and I define a Reynolds number which is the upstream speed u infinity into this length of the plate by the kinematic viscosity of the fluid, then when we talk about high Reynolds number flows, we mean that this is much greater than 1, or mathematically you can say we are taking the limit R e approaching infinity. Now, we have seen that a boundary layer will grow over the plate and the boundary layer will remain thin when the Reynolds number is large. Now, we have looked at the flow inside the boundary layer. This cannot be an irrotational flow. We will look at it later, but we will show that the flow outside here, which we will call the outer region, we will show that the flow in the outer region is irrotational, and then you will understand the utility of studying potential flows for predicting the flow of real fluids. Now, if I say this is y equal to delta x, we showed yesterday that if the order of delta x is delta naught, then delta naught by L is of the order 1 by root of R e, and this is going to be much less than 1 when R e is much greater than 1. So, this thickness is much less than the length of the plate. So, the viscous effects we argued will be important only in this layer and will not be important in this layer. So, we will show that by an order of magnitude analysis today, and we will prove that the fluid flow in this region can be described by a potential flow analysis. Now, yesterday we took a point which was inside the boundary layer, and when we did the order of magnitude analysis, we argued that its distance from the wall, the y distance, the normal distance, is much smaller than the distance is from the in the x direction from the leading edge. And by anticipating that, we did order of magnitude analysis and found out this estimate that delta naught by L is much less than 1 of the order, sorry, delta naught by L of the order of 1 by root of R e. Now, we will consider a point somewhere here that is far away from the plate. So, we will consider y p also to be order L as well as x p order L. That is, if I look at its distance from the origin in the x direction and the y direction, they are comparable if p is a point in the outer region. So, yesterday we had looked at a point p which was inside the boundary layer. So, there again x p was order of L, but y p was much less than L. Now, let us look at the order of the functions in the outer region. So, I will draw another figure. We are considering a point P in the outer region. So, in the outer region, which is far away from the solid plate, we are saying x is order L, y is also order L for any point P in the outer region. Now, we know that the upstream flow is a uniform flow with a magnitude of the velocity which is u infinity. So, the speed is u infinity. So, we know that in the outer region u will be order of u infinity. Now, v is 0 upstream. So, from the upstream condition we cannot find what is v. So, let us say that v is order of some say v 1. I have used v 0 for the velocity scale in the y direction inside the boundary layer. Now, I am using a different symbol. Now, as before we will define non-dimensional coordinates which are order 1. So, we will have capital X to be x by L. So, this is order 1. Now, I have used the symbol capital Y to denote y by delta naught. So, here I will use a different symbol. I will use the symbol y star to denote y by L. So, in the outer region this y star is order 1, and in the boundary layer, let me emphasize, if you consider y star to be y by L for any point inside the boundary layer, this is of the order of Re minus half, which is small, and we have defined capital Y which was y by delta naught. So, this we can call y by L into L by delta naught, or y by L by delta naught by L. So, this is y star by something which is order 1 by root of Re. So, if y star is order root of minus half and the denominator also is root of minus Re, then this is order 1 inside the boundary layer. But if you look at y star for a point inside the boundary layer, it is small, but if you have a point in the outer region, then y star is order 1. Now, del u del x I can write as u infinity by L into del of capital U del capital X. The reason being u is okay, I did not define capital U, I had done it yesterday. Capital U is say u by u infinity. So, this is order 1. Now, if I say small u is u infinity times capital U, you get this term u infinity over here because it is a constant, and small x is L times capital X. So, this is L over here. Now, we are going to assume that because this capital U is the order 1 function and capital X is the order 1 function, that this quantity del of capital U del x del of capital X is order 1. So, that means this quantity here u infinity by L gives you the order of magnitude of del u del x. Now, we will define V, sorry, I have used capital V to be v by v naught yesterday. Now, I will define v star to be v by v 1, where v 1 is the velocity scale in the normal direction in the outer region. So, this is order 1 in outer region. Now, if I say that y star is y by L and v star is v by some v 1, then del v del y I can write as v 1 by L into del of v star del y star. So, this L has come from this y, because y is L times y star, and this v 1 has come from here, that v is v 1, that constant velocity into velocity scale into v star. Now, once again we are going to assume that this is order 1. The rationale for this is that y star is order 1 in this coordinate, and we are saying that the v 1 scale is such that v star is order 1 in the outer region, and our goal now is to determine what is v 1. Okay. Now, we have seen that del u del x is minus del v del y from the continuity equation. That means that absolute value of del u del x is equal to absolute value of del v del y. So, del u del x and del v del y must be same order of magnitude. So, this we can also write in this fashion: del u del x plus del v del y equal to u infinity by L into del capital U del x del capital X plus v 1 by L del v del y. Now, this quantity u infinity by L gives you the order of magnitude of del u del x, because we are saying that the scale variables are all and the derivatives are all order 1. Similarly, v 1 by L gives you the order of magnitude of del v del y, because this is a scale quantity which is order 1. Now, order of del u del x and order of del v del y must be the same, as I have argued over here. The reason being this is equal to 0. So, one is the negative of the other. So, therefore, u infinity by L must be order of v 1 by L. So, without loss of generality I can say take v 1 to be u infinity. Now, let us go to the momentum equations. So, we will write the momentum equations in non-dimensional form, and we have found the scales for the order flow. So, we have capital X is x star by L, sorry, capital X is simply x by L, y star is y by L, u is u by u infinity, and v star is v by u infinity. Likewise, we will define p star to be p by rho infinity square. So, this p star, capital X and capital U are the same non-dimensional variables which we have used when we analyze the boundary layer. The two new quantities are y star and v star. So, our argument is that in the outer region all these non-dimensional variables are order 1. Capital X is order 1, capital this y star is order 1, u is order 1, v star is order 1, p star order 1. Now, let us look at the x momentum equation. You are going to have rho times u del del x plus v del del y acting on u equal to minus del p del x plus mu into the Laplacian of u, which is del 2 u del x squared plus del 2 u del y squared. Now, we will introduce these non-dimensional variables which are order 1, and the first equation I will write as, sorry, the first term on the right hand side I will write as rho u infinity squared by L into u del u del x. So, this u infinity is coming because there are two velocities, and this L is coming because there is one x here. Now, once again we are going to argue that the scale variables are order 1, that means the order of rho u del u del x is reflected by the coefficient rho infinity square by L which is sitting in front of this term. Now, let us write the second term. Second term will have the same factor rho infinity square by L, and it will be multiplied by V capital V, sorry, not capital V, V star del capital U del y star. And once again this is going to be order 1. Now, since both the velocities u and v are scaled by the same quantity u infinity, you are getting u infinity square here, and both the non-dimensional variables coordinates x and y star are the dimensional x and y scaled by the same quantity L, you are getting L over here. So, you can see that these two terms are same order of magnitude. Now, let us write the first term on the right hand side. Now, P I can write as P star into rho infinity square. Rho infinity square being a constant, you are going to have rho infinity square by L into del of P star del x star, and once again this quantity, the scale quantity we are going to say is order 1. So, therefore, the order of del P del x is given by rho infinity square by L. So, if we compare the two terms on the left hand side with the first term on the right hand side, you will see that these three are the same order of magnitude. Now, we are doing all this to see whether certain terms in the equation can be neglected in comparison with other terms. So, conclusion is either all three have to be retained in the approximate equation or all three have to be ignored. Now, let us look at the viscous term over here. Now, here both of them are same order of magnitude because the x and y coordinates are scaled in the same way, and you have u over here. So, you are going to have over here a term which is mu u infinity by L squared into del 2 u del x squared del capital X squared. That is the first term, this is order 1, and the other term I will write below, which is mu u infinity by L squared into del 2 u del y star square, and this quantity also is going to be order 1. So, you see that the order of the inertia term is rho infinity square by L, the order of the pressure net pressure force is the same order rho infinity square by L, and the order of magnitude of the viscous force is mu infinity by L square. Now, if you look at the ratio of the viscous force on the particle by the inertia force. By inertia force we mean the negative of the mass times acceleration. So, in this equation this is mass times acceleration per unit volume, and this is the net viscous force on the particle per unit volume, and this is the net pressure force on the particle per unit volume. Now, since the volume of the particle is the same, if you want simply the forces, ratio of the forces, this is the same as the ratio of the forces per unit volume. So, this order is mu u infinity by L squared divided by rho infinity squared by L. The reason being both the viscous terms are of the order mu u infinity by L squared, and both the acceleration terms here are order rho infinity squared by L. Now, what you find is that this quantity I can write as mu u infinity by L squared into L by rho u infinity squared. Now, this U infinity will cancel with one of this square term, and this L will cancel with this square term. So, what you are left with is mu by rho U infinity L, or you can also write it as nu by U infinity L, which you recognize as 1 upon R e. So, we come up with a familiar interpretation of Reynolds number, which is the inertia force by viscous force on a particle. Now, this interpretation is true for a point in the outer region. If you look at a particle which is inside the boundary layer, this estimate is not correct. There the viscous force is of the same order as the inertia force, and that is what we used when obtaining the boundary layer approximation yesterday. But in the outer region, we see that the viscous force is much less than 1 if R e is much greater than 1. That means, if you are looking for an approximate equation which is easier to solve, and if you go back and look at this equation, what you would do is you will drop these two terms, both the viscous terms. You may recall that in the boundary layer approximation we dropped only this term. This was important. If you drop both the terms in the boundary layer analysis, then again you will come up with a contradiction that the drag is 0. So, here what will happen is you have an approximate equation, that is rho times u del u del x plus v del u del y is approximately equal to minus del v del x. I have written it in dimensional form. Now, this is the approximate x momentum equation. So, this is balance of momentum in x direction. Or if you want to be very precise, you can say approximate balance of momentum in x direction in the outer region. Now, you will recognize this as the x component of Euler's equation of motion. So, that means here although there is a viscous fluid, the viscous forces are negligible and is behaving like an inviscid fluid. So, you can call it an inviscid flow. The shear stresses here are small, and the physical reason for this is that if you look at the velocity profile, so this is a plate, at this section the velocity profile has a shape like this, a sharp gradient in a layer, thin layer close to the wall, which we call the boundary layer, and here the velocity is almost uniform. So, del u del y is very small here. So, the shear stresses here are small, the shear stresses are due to viscosity. So, viscous stresses are small in the outer region, and the fluid is behaving like an inviscid fluid, and the flow can be adequately described by this Euler's equation. Now, you can do a similar analysis in the y direction and come up with the Euler's equation in so if you look at y momentum equation, the analysis is similar. So, I will not waste time in repeating it. You are going to have rho times now u del del x plus v del del y acting on v. So, this quantity in square brackets is the material derivative of v, approximately equal to minus del p del y. So, let me summarize the approximate equations in the outer region. Now, you have to be patient with this mathematics, because this will give you a physical insight into how the fluid flow behaves. And if you want to explain things like phenomena like boundary layer separation, then you need to know all this. So, the continuity equation is simply del u del x plus del v del y equal to 0. This is for 2D incompressible flows. There is no approximation here. The x momentum equation is rho times u del u del x plus v del u del y equal to minus del p del x. So, this p is a piezometric pressure. So, if I use this, it means that the body force has been accounted for in this, and the y momentum equation is rho u del v del x plus v del v del y equal to minus del p del y. So, as you can see, there are 3 unknowns in this set u, v and p, and you have 3 equations. So, it can be solved in principle, but they are coupled. So, it is a system of equations. So, in this equation u, v, p are all appearing, here also u, v, p are appearing, here p is not appearing, but u and v are appearing, and they are nonlinear, because if you look at this, you have product of velocities which are unknown. So, this for example can be written as del del x of u square by 2. So, the left hand side is a nonlinear term. Now, although it is nonlinear, we will show that you can find the velocity field by solving a linear equation. So, first of all, what we will do is we will try and eliminate pressure from these 2 equations. Now, the way to do it is to take the x momentum equation and differentiate it with respect to y partially. Then right hand side you will have a term which is delta p del y del x. Now, you know that delta p del y del x is the same as delta p del x del y. So, we will differentiate the y momentum equation with respect to x, and then we will subtract the 2, that will cancel out the pressure term. So, let us do it patiently. We will look at first of all del del y of x momentum equation. And see what this tells us. So, if we look at del del y of the left hand side of x momentum equation, you are going to have del del y of rho u del u del x plus del del y of rho u rho v del u del y. Now, the first term I can write as rho is a constant for us, rho into del u del y into del u del x, and the second term I can write as rho u del 2 u del y del x. So, these 2 terms in square brackets, which I have written in blue color, come from the first term here. You have a product of 2 functions. So, when you differentiate it, you will get 2 terms. The first one is the derivative of the first function into the second function, and the second term is the first function into derivative of the second function. So, when you differentiate the first function, we get del u del y, and del u del x remains as it is. When you differentiate the second function, you have del 2 u del y del x, and here the first function remains as it is. Now, I will write in orange the 2 terms which will come from here. Rho is a constant, so you have rho times del v del y into del u del y plus rho into v into del 2 u del y square. Now, let us look at these 2 terms. Both of them have a common factor, which is this del u del y here. So, if I factor that common factor here and write it as rho times del u del y, you will have del u del x plus del v del y, and then you will be left with the other 2 terms. But before we go further, you will notice that these 2 add up to 0, because of del u del x plus del v del y is 0 from the continuity equation. So, out of the 4 terms, 2 of them will cancel out. Now, this term I will write as rho u del 2 u del x del y, So, here we have assumed that u del u del y and del u del x are continuous functions. So, the order of differentiation in this mixed derivative does not matter, and here we are going to have plus rho v del to u del y square. So, these two I can write as rho u del x acting on del u del y and rho v del y acting on the same quantity del u del y. So, if you wish, you can write this in compact form rho v dot grad of del u del y. We will not need this notation, but I am giving you the motivation why we have switched the order of differentiation here. We are able to write it as this convective derivative v dot grad acting on the same function del u del y. Now, we can do a similar thing. Okay. Now, before we go further, let me write down what is del y of the right hand side of x momentum equation. This is going to be del y of minus del p del x. So, I will write it as minus del 2 p del y del x. So, the final result that we get when we differentiate the x momentum equation with respect to the other coordinate y is that rho u del x acting on del u del y plus rho v del y acting on del u del y is minus del 2 p del y del x. So, I will put a box around this and we will use this later on. Now, what we will do is we will look at del x of y momentum equation. So, we will take the y momentum equation and differentiate it with respect to the other coordinate x, and let us see what you get. Now, del x of left hand side of y momentum equation will be del x of rho u del v del x plus del x of rho v del v del y. Now, I will go a little bit faster. To this term I can write as the sum of two terms rho del u del x del v del x plus rho u del 2 v del x square, and the other two terms I can write as rho del v del x del v del y plus rho v del 2 v del x del y. Now, once again, if you compare this term with the third term over here, you will see that del v del x appears in both the terms. So, if you factor it out, you can write it as rho times del v del x into del u del x plus del v del y, and once again you will note that these two terms will add up to 0. So, out of the 4 terms again 2 cancel out, and the other 2 terms I will write this way rho u del 2 v del x squared plus rho v. Now, here once again I will interchange the order of differentiation and write it as del 2 v del y del x. So, what we can do is I can write this as rho u del del x acting on del v del x, and the other term I can write as rho v del del y acting on the same variable which is del v del x. Now, if you look at del del x of right hand side of y momentum equation, this is going to be del del x of minus del p del y, which I can write as minus del 2 p del x del y. So, when you take del del x of x momentum equation, you come up with this result that rho u del del x acting on the variable which you have seen here del v del x plus rho v del del y acting on the same quantity del v del x equal to minus del 2 p del x del y. So, we will compare this equation with the previous equation which you have, and I will put a box around this. Now, let us call this equation Roman 1 and I call this Roman 2. You will see that on the right hand side here you have the mixed partial derivative del 2 p del y del x, where you are first differentiating with respect to x, then with respect to y, whereas on the right hand side of this equation which I am called Roman 2, you have the same mixed partial derivative of p with respect to x and y, but the order of differentiation is reversed here. First you are differentiating with respect to y, then you are differentiating with respect to x. But again, if p del x and del p del y are continuous functions, these two are going to be equal. So, if I subtract one from the other, just a correction, this is del x of y momentum equation. So, if you take equation number Roman 2 minus equation Roman 1, let us see what this gives. Well, the right hand side will cancel out, and the left hand side you will see is rho u del x operating on this difference now del v del x minus del u del y, and the second term will be rho v del y acting on this difference del v del x minus del u del y. So, I am going to have rho u del x acting on del v del x minus del u del y plus rho v del y acting on del v del x minus del u del y equal to 0, and you will recognize this quantity here as the z component of the vorticity which we are calling omega. So, when we eliminate pressure from the two momentum equations, we get an equation for transport of vorticity. So, vorticity transport equation in the outer region is u del omega del x plus v del omega del y equal to 0, or you can write it as v dot grad acting on the scalar omega or omega z if you want to emphasize that it is a z component of velocity equal to 0. Now, if you do a similar analysis for the Navier-Stokes equations, you will have a diffusion term which is nu into Laplacian of omega in 2D flows, but that term, the viscous term, is negligible in the outer region. So, you have simply an inviscid balance. Now, let us consider a streamline in the outer region. So, this is a plate and you have a thin boundary layer. We will consider a point P in the outer region and look at the streamline, which we expect to be like this, because the fluid is displayed outwards. If you had fully inviscid flow over the plate, then this streamline would have been parallel to the x direction, but because of the displacement effect of the boundary layer, it is going to be curved and pushed outwards like this. Now, if I have a point here, or let me take 2 points on this side, say P and Q. If I say that I draw this triangle over here, this is the point P, this is point Q. If I say this is dx and this is dy and this is say ds, arc length along this point. So, let me draw an enlarged view. This is the point P and this is the point Q on the streamline. This arc length along the curve we are calling ds. This is almost tangent to the curve. So, it is like a straight line, and this I can call dx and this is dy, and if you want this angle you can call theta. Now, we know that if I draw the velocity vector here, it is going to be tangent to the streamline. So, tan theta, which is dy dx, is v by u. So, you have this relation that dy by v is dx by u. Or if you look at the sine and the cos separately, if you look at cos theta, that is dx by ds from this triangle. Okay. Now, I can draw another triangle here where this much is u and this is v. So, cos theta is also going to be equal to u by the magnitude v. So, you have from here dx by u is ds by v. So, the equation of the streamline you can write as dx by u is dy by v is ds by capital V, and this capital V of course is root of u square plus v square, and s is arc length along the streamline. So, what you can see is that dx I can write as u by v ds, and dy we can write as small v by capital V ds. Okay. Now, if I want d omega, the change in the vorticity between the point P and the point Q, you know from calculus, because omega is a function of x and y, this is del omega del x dx plus del omega del y dy. Now, dx I can write as u by v ds. So, this quantity I can write as del omega del x into u by v ds, and the other term we can write as del omega del y into u by v by v ds. So, this can be written as, if I factor out the 1 by v, u del omega del x plus v del omega del y ds. So, we can factor out the ds by v. I have written the ds on this side and the 1 by v here to put it in a neat form, but what you see is that you have u multiplied by del omega del x plus v multiplied by del omega del x. Now, we have shown that this quantity is 0. That means, g omega is 0 along between the 2 points on the same straight line. That means that omega is a constant, omega is a constant along a streamline. Now, let us see what is the physical implication of this. I will draw the plate again and show the boundary layer over here, and you have a streamline which is going to be curved, and here it is going to be parallel to the x direction. So, this is a steady flow, the streamline and path line is the same. So, the fluid particle which is here is going to move along this and come over here and then move this way. Now, we are saying that omega is constant along this streamline, and upstream is a uniform flow where u is infinity not at one point, but at several points. So, we know that in this particular region over here omega is 0. So, that 0 value will be conserved and this constant will be equal to 0. So, if you have a upstream flow which is irrotational, you can take any streamline which is starting from this region with a 0 omega, again omega will be a constant over here and it will be 0. Now, if we take a fluid particle which is entering the boundary layer, well, here again omega is 0, but once it enters the boundary layer here omega will not be equal to 0. So, inside the boundary layer you are going to have a relation u del omega del x plus v del omega del y approximately nu del 2 omega del y square. This viscous term will cause a change in omega along the streamline. So, some vorticity will be generated by the effect of viscosity. Now, why vorticity will be generated we will discuss after the lunch break. So, we will take a break for about 1 hour.